roots. Right? MATLAB does great for that. If it's symbolic, what do we do?
Route array.
Route array. And that's a method of determining where roots are. So we've got a little bit more definitions of stability. One of them is global stability. It's not politics, but for systems, there is no global stability. Right? What does that mean, do you think?
Maybe feeling all parts of the system are stable?
Also, or the entire space is stable. Entire, in this state, we're talking about the state space. For all of our variables, the entire thing is stable. Right? Basically, one way to think of it, as time goes to increases, the system doesn't go to infinity. Right? Our picture, our projector cuts off the last part there. It shows up here, it doesn't show up there. Sorry. Basically, it doesn't go to infinity. Okay? What does that allow? And your definition was a good one, which is says, given some perturbation or some starting point goes to equilibrium. But what does this allow?
Oscillation.
An oscillation, a sustained oscillation. Right? That says that's stable. Right? We have systems that are oscillatory, that are stable. Right? We are. Right? We have heartbeat, we've got circadian rhythms, all these things are oscillatory, yet hopefully stable. Right? Until they're not stable, and then you're off in the other global realm. So that says the sustained oscillation is okay. Right? Then there's asymptotic stability, which is what we're talking about. It says, given something, it's going to return to the, let's cut off their origin. Right? So in this case, is a sustained oscillation stable? It's not asymptotically stable, but it might be globally stable. Right? All right. What's this mean? BIBO. Bounded input, bounded output. We talked about that in our early controls classes and things. What does it really mean? Yeah.
Means that like for any real input, you get real output that doesn't go off to infinity.
Bounded means limited input.
Yeah, limited.
Yeah. It could be real, but infinity is real. Means I have a limited input. My output will also be limited. Right? What's an example of a non-BIBO system? Talked about this in the 5200, 6200 class. If I have my roots right on the imaginary axis, is that BIBO stable?
Yes.
Not necessarily. Think about this. If I have my roots that are purely complex, example J Mesa, right? What's that represent in time domain?
Sinusoid.
Sine cosine. Right? What if I have a system that excites right at that frequency? This would be the natural frequency. So the system excited right at natural frequency. What's the output?
Resonate to infinity.
Goes to infinity. Right? You've seen this type of clock where you have mass, spring, no damping. Okay? Natural frequency is, of course, variable P over M. Root for this, or the differential equations is. But excited right at that natural frequency. Well, it goes off to infinity. So I got bounded input. Some sine wave doesn't go to infinity. But my output magnitude does go to infinity. But that is not BIBO stable. Bounded input, but unbounded output. Right? Now, for the linear system, that's usually about the only case we have that's a problem. But not the case for a nonlinear system. Nonlinear systems, you don't necessarily have nice behavior curves. We'll talk about some nonlinear stability. The other one is called internal stability. Basically, it's a homogeneous system, homogeneous differential equation, stable. That's when it says all the real roots have to be negative for the characteristic equation. Right? Homogeneous equation, remember the differential equation equals 0. Right? Don't forget that one. It's a characteristic equation. That says all of my roots of that thing are stable roots. Right? I don't get any exponentials going off to infinity. Right? Over time. That's what we typically always talk about. If you really think about this, the fundamental idea is that the energy of the system is decreasing. Right? Is the energy increasing, staying the same, or decreasing? Right? If the energy is increasing, it's what?
Unstable.
Unstable. If the energy stays constant, it's possibly oscillatory. Right? If the energy is decreasing, it's asymptotically stable. Right? So, that brings up this idea that the energy at the end of our time here minus the energy at the beginning must be less than 0. Or you might say more restrictively, take the derivative of energy over time, we want it to be negative. So it be equal. Look at an example. Simple mass spring system. We'll put some friction on it. Right? Another differential equation to this guy. Well, in fact, what's the energy for it? Here's the differential equation for it in state form. Right? Or I say x1 dot is equal to x2 dot is equal to b times the velocity minus k times the position. Right? Hopefully you can get a state equation for a simple system like that now. And we'll assume K and B, well, K is some nice number. B could be a constant, right? Nice viscous friction. It could be some function of time, right? Or, whoops, being cut off here. Basically, it says B is some alpha absolute value of x. And that should be equals 2. What's that? What kind of friction?
Static friction?
Constant, yes, it's some constant friction. Okay, yeah, we got some kind of constant friction going on. Okay? All right, let's look at this thing, and then what's the energy of this system? How could I describe the total energy of the system? In terms of what? Well, in a spring, we have a mass. Right? Yeah.
Kinetic potential energy?
Yeah, total kinetic potential energy. All right, kinetic energy, 1/2 mv squared, x2 is velocity, 1/2 k, x1 is position. All right, that's the total energy of the system. All right. Okay, or, well, look, red matrix form. And then let's get cut off here. This is x1, x2 over here. But I can write this thing as some x transpose, some matrix R which contains k over 2, v over 2. All right. But it should be m over 2, sorry. All right. Error. Notice that error before. I'll fix that. Derivative of that is this. Derivative of the energy, m x2, x2 dot, plus k, x1, x1 dot. All right. Take the derivative of total energy. And if it's stable, we're saying what? Should be negative without this. And we've got these derivatives here. Well, let's use the state equations to get rid of x2 dot and x1 dot. So state equations, x1 dot is equal to x2. x2 dot is equal to the state equations. All right, get this. Derivative of the energy, to put in the state equations for x2 dot, state equations for x1 dot. And I don't have any derivatives there now. Everybody follows? All right. Do up all the sums here, and that's equal to minus b x2 squared. Everything else drops out. Okay? So what does that say? That the derivative of the energy is negative the frictional constant times the velocity squared. Is it always negative? We want the dE dt to be less than 0. It means I'm decreasing energy. Is that always decreasing energy?
Yes.
It depends what b is. Because x squared, it doesn't matter what x velocity direction is, all squared. It might say, but it matters what b is. Okay. Okay, so if this thing b is greater than 0, stable, right, no problem there. If the time function of b is greater than 0, we're stable. So basically our friction could vary over time, which does happen. As long as it's positive, we're still stable. And as long as alpha is greater than 0, we're stable. Okay? So the system will be asymptotically stable if those conditions hold. Okay? Another example, same kind of system here. All right? What the forces in this thing now, we're going to use kind of the long graph, linear graph method. What the forces in this guy. Put the state equations in. We have similar, except I have, well, my friction is this crazy form, which is nonlinear. Nonlinear friction here. Right? So I have nonlinear differential equations. So I have some gamma 1 minus the position squared times the velocity is the force of the friction. So the friction is changing with position. Okay? Still got state equations down there. Notice the m cut off there. Okay? Find the energy. Wow. Energy is a little bit trickier because say I have nonlinear string here too. It's a cubic string. All right? So the spring constant goes not just as x, but as x cubed. All right? What kind of spring is that we call? It's not linear. It's used a lot. It's used in car suspensions. It's called so-called hardening spring. So the more and more it gets, the stiffer the spring gets. Your car springs are actually like that. Right? They're kind of soft for middle range. They get stiffer the more they're compressed. And that's to prevent bottoming out of the car. So it's a so-called hardening spring. You have a question?
Yeah, I just want to double check and make sure because I'm not getting this right now. These are just force equations that
Yes.
you put in.
So I got the state equations using some of the forces in this thing. Get state equations saying derivative of positions, velocity. Derivative of velocity is, well, this nonlinear function here.
Okay.
But still got state equations for the darn thing, right? Even though they're nonlinear. Now the energy you got to figure out in this thing. Kinetic energy is simple. The potential energy of the spring, I need to do the integral. Basically, I'm doing the work. So this is the force, F K1 cubed dx. Integrate that. That's the total work done, which is the energy. Right? So same as you did in dynamics, work equals energy, but I have to do this integral because it's not linear. Solve that, I get this. All right, so the energy is, kinetic energy is kind of the same, but this potential energy is 1/4 K x 1 to the 4th power. All right? All right. Take derivative of that. All right, well, same thing, but I can then put in the state equations for x1 and x2 dots. Right, put those in, you get this. So this is for x2 dot, for x1 dot. All things. And it's stable if this energy decreases. All right, so what's the condition for dE dt to be negative? We try to reduce this whole thing. x1 squared is always positive, x2 squared is always positive. Got a minus sign here, but assuming gamma is positive, remember, x1 must be what?
Negative.
Negative.
Between negative 1 and 1.
Less than 1. Yeah, bound by minus 1 to 1. As long as my position is within minus 1 to 1, I'm stable. But outside of that, I'll be unstable. Right? That makes sense? So you can even handle nonlinear systems to determine stability by this energy method. Right? Now, the Russian fellow, turn of the century, that's the turn of the 20th century, Lyapunov, looked at this issue and determined what's called Lyapunov stability. And so it was 1882 he did this, and this is his so-called second method. And it comes to this idea that if the energy is decreasing, the system's stable. And it works for nonlinear time-varying systems, any kind of system. Right? So it's a very powerful system, method. In fact, if you take nonlinear controls, they'll spend quite a bit of time on Lyapunov stability. Right? Determining all different ways of determining regions of stability and things for all nonlinear systems. And it can get kind of hairy for a while, but it's really very powerful technique. And it also guarantees stability or instability. Okay. So, Lyapunov generalized this idea of this energy, but instead of energy, he used some arbitrary scalar called Vx. That's of the states. Right? So, energy, of course, is a scalar, right? Energy is a scalar. And Lyapunov says, well, you know, it could be an energy. In fact, energy is a Lyapunov function. Right? It's a special case of a Lyapunov function. But he says, in general, if I can find some function here, I can prove stability. Using essentially the same ideas. So this is if and only if these are the conditions. The Lyapunov function at the origin, that's when all the states are 0 for any time, it's going to be 0. Right? So is that the case for energy? So kinetic energy, if velocity is 0, is the energy 0? Yeah. Potential energy, if the position is 0, is the energy 0? Yeah, for all time. So that's a satisfies that. And then this Lyapunov function for any state, any time, must be positive. Same as the energy. Kinetic energy is always positive for any velocity, any time. Potential energy, positive for any position, any time. Right? That fits that condition. Then the last one is the derivative of this must be negative, which will show energy does that. Actually, this is like energy, but it's not necessarily is energy. And if all those conditions hold, it's stable. Yeah.
Wait, so this V, it's velocity or is it?
No, it's a scalar.
Okay.
Some scalar function.
Okay.
And it's a function of all the states in time. So energy is an example of one of these functions.
Okay. And what are the two variables there, the 0 and the t or the x and the t?
These are the states. So it says if all the states are 0, for any time, the Lyapunov function must be 0.
Okay.
For any state, any value of any state, any kind of Lyapunov function must be greater than 0, must be positive. And the derivative of it over time must be negative. Okay? Make sense? So energy is a great example of this. It fits all those criteria. Yeah.
I think you just answered my question.
Yeah.
I was going to ask how you pick the function.
That's the hard part. We'll get into that. Yeah. It works great if we can figure out what these functions are. And that's not always trivial. Like wherever it is. There's a converse to this. It says, okay, first condition, Lyapunov function is 0 for 0 states, positive for any states, less than 0. Whoops, I didn't take the wrong one. I did this. Reverse these signs.